Okay, so today we're talking about how to break ARM64 servers. So I presented an ARM talk last year at the same conference, and there I talked about the success we made while trying to port to a different CPU architecture. Now we're going to talk about failures. Okay, so a little bit about myself. I do performance and security at Cloudflare. I'm passionate about cryptography, and I also am a fan of low-level programming, so Linux kernels, bootloaders, core user space services, so any low-level stuff. Okay, so this is how our initial ARM64 integration looked like. Originally, when you have a server, you quickly rack it in a data center, you'll get a picture something like that, because you need software to run there, and you have no ARM64-based software, so you need to compile. So what you do, you go to your developers and say, hey, can you please compile all your software to ARM64? And one of the first issues you will encounter that the developers will say, but how do I do that? Because you have your ARM servers, but I still have an x86 laptop, right? So there is a solution. You say, yep, you can cross-compile stuff. Who doesn't know what a cross-compile is? Everyone know? Well, I'll quickly recap. So this is a regular compiler. So assuming you have a simple C source file, you have your x86 developer laptop, you have your compiler, you feed it the source file, it produces you a binary which you install into your production, right? And you can also run this binary on your laptop. The cross-compiler is a bit different, so you still have your x86 laptop, which runs your cross-compiler, but it produces a binary for a different CPU architecture, which you run on your ARM64 production servers, and you can't run it on your laptop. So the reason I'm introducing cross-compiler is because I need some terminology to explain the failures later. So in cross-compiler terminology, you have a host, which is the CPU architecture on which the compiler runs. It's usually the developer laptop architecture, right? And you have a target. It's the CPU architecture for which the compiler produces machine code. It's your production. It can be x86 or it can be ARM64, right? And like in particular, there is a specific case where host architecture equals target architecture. This is a normal compilation, which is just a subset of cross-compilation. So the way how it looks in your development environments, assuming you compile your source file to a binary. If you do a normal compilation, you just invoke GCC. You can inspect the binary. It's for x86 architecture, and you can run it. To compile the same binary for ARM64 cross-compile, you just replace your GCC with GCC, which is a cross-compiler. You can inspect the binary. It's ARM64 now. And you can't run it because your x86 developer laptop does not know how to run this ARM64 code, right? So this is easy. So it seems easy, but when you have a bigger, on one file, right? But when you have a bigger project, sometimes you have more issues because you have a complex build system which invokes compilers under the hood, and you ended up, and if you didn't expect that you will be using cross-compiler at some point, you may encounter these different things when compiling your projects to ARM64. So, and when you ask developers to do it, they will probably say, yeah, they will probably never work because there's a lot of assembly in the code for x86. So this is mostly not true. From the hundreds of packages we ported, we never encountered that we couldn't port the package because of assembly. So it's always something else, but not assembly. Most software is pretty cross-platform nowadays. So the first thing we encountered is we can't compile software for ARM. And we tried both cross-compiling and also natively compiling it for ARM on an ARM64 server. And both builds are broken. And you get some error like this. So you unrecognized command line MSEE2. So the cause here is when somebody designed the build system, they used this flag, which is x86 specific. And if you feed it to x86 GCC, it will consume it. If you feed it to an ARM GCC, ARM doesn't know what to do that. So it usually looks in your makefile something like that. And GCC is designed in a way, if it can't recognize the flags, it will just fail, right? So your compilation fails. So the advice here for developers is put architecture-specific flags in different variables with architecture-specific variables, each for one architecture. So to properly write it, so you will have C flags for x86, you have C flags for ARM64, which are different, and then when you compile, you just take whatever the target architecture you're compiling to. The second potential pitfall we encountered is only cross-compiling is broken. So native compiling for x86 works, native compiling for ARM works, but when you try to cross-compile in the CI, it fails, right? And it usually happens when the compiler output is not enough to produce the final artifact. You have a post-processing tool which converts the compiler output to a different format. And this post-processing tool is also included as part of the package in source form. So your build system compiles the target code, compiles the post-processing tool, and then uses the post-processing tool to process the final artifact. The error will look similar. You also get this unrecognized command line option. So the overall build systems look something like that. You have sources, you have your target GCC cross-compiler, you process the sources, you get intermediate artifacts. Then you have the tools you need. You process it with the host GCC compiler because you need those tools to be used in the build system. You get the output of the compiler, and then you process, at the last step, you process your artifacts with your compiled tools, and you get your final artifacts. So the cost here is you use C flags everywhere, and you should distinguish between target C flags and host C flags. Or you use some other additional flags variable which is not target or host specific. And we encountered this issue with trying to compile the IPXC, the bootloader we use in production. Their build system supports cross-compilation. They designed it for cross-compilation, but it just doesn't work because of this. So their problem was they're using these called workaround flags, which are determined automatically based on the target architecture, but they appended to target C flags and host C flags. And when you try to compile this, you get this error unrecognized flags. So the advice here for developers is put your architecture-specific flag in a separate variable as before, and also always prefix all your flags with target or host, like with the intent to which either use for the target compiler or with the host compiler. So don't do workaround C flags, do target workaround C flags and host workaround C flags. If you do have, I don't know, common architecture independent flags, put them explicitly in the common C flags variable. So DevOps can help here as well. Based on these advices, you can provide the tools and support to test cross-compilation in the CI. So for IPXC project, if they actually tested their cross-compilation build system, they would find this bug. It's very easy to find. And also, based on the advice given above, you can design linters to actually enforce the proper design of the build system that each C flags variable needs to have prefix target or host. So you explicitly know whether these flags go to the target compiler or host compiler. Much easier to debug. The downside is sometimes you get slower compilation times because you're testing both compilation and cross-compilation, but I think it's a feature, right? Because you give your developers a little bit time to take a break. The final potential pitfall we encountered is broken artifacts. The cross-compilation works fine, but in the end, the artifact itself, when you install them to the target system, don't work. And again, as before, it usually happens when the compiler outputs needs additional post-processing tools. These tools are part of the sources as well. But also, these post-processing tools are also included as a release artifact. And you get error something like that, cannot execute binary file, exact formatting of fixed depth. So we encountered this issue when cross-compiling Linux kernel, pretty much unpopular project. And the reason here was incorrect usage of host compiler versus target compiler, or incorrect build dependency declaration. So this fixed depth tool, we need to build it for both for target architecture and host architecture. But maybe Makefile sees that we already built this tool as part of for the host architecture and never tries to rebuild it in for target architecture. So if you basically cross-compile vanilla Linux kernel and use its scripts for Debian packaging, you will have broken Linux headers package. So this fixed-dep tool is used to post-process kernel module. So you need the host version to do it when you're in the build system, when you build in the Linux kernel. And also you need the target version in this package, because this package allows third parties to build modules for the running kernel. So in this package needs to go for ARM64 architecture, but for Linux build system, put an x86 version there. So yeah, the overall picture looks similar, but you kind of have this additional step that both the final artifacts and tools go to extra packaging. Yeah, and fixed-dep means because on ARM64 we tried to execute x86 binary, so that's why you get this error. So for developers, ensure that all target artifacts are processed with target cross-compiler. And what I've seen a good practice in many embedded projects, including Android, if you try to compile Android from source, they always put output in two directories, like host and target, and like they produce artifacts from the target directory. So if you don't have anything you need as an artifact in target directory, probably you're doing something wrong. It's very easy to navigate. For DevOps, you again provide tools and support to test cross-compilation in the CI. And additionally, you can also inspect the final artifacts for anomalies. Like we can have a check, like why this Debian package for ARM64 architecture contains x86 executable. Doesn't make any sense. So these were all compile time problems. So now we're finished with compiling. Everything compiles. We try to run it. Now these are runtime problems. The first problem you may encounter is when you start your process, it complains about not being able to allocate memory. We have a huge selection of memory management now. It can have many implications, but it's much simpler in this case. And when you check, there is a lot of memory, free memory in the system. There is no pressure and everything. Everything is fine. And most likely, your process uses a map syscall for I/O. You don't have to know if it's using map. If you just trying to run some database and you get there, it's probably using mmap, so it's most database workflows. And you get error something like this, like mem cannot allocate memory. To understand what happened here is we need to go a bit to basics. Why we moved to 64-bit system? Because 32-bit systems allows you to address only 4 GB of RAM, right? And 64-bit allows you to address up to, whoa, like this big, huge number. Well, we can say just more than enough, right? Right? Wrong. The cake is a lie. The operating system, all operating systems cheat you, and they take away your resources. So this is how virtual memory map is set up on Linux, on x86 platform. So you have the user space addressable range, you have the huge unused hole, and you have the kernel addressable space here. So this is where I take it from. So actually, your user space application can only use this range. So not 60. Also, you only can use the 47-bit of addressable space, which gives you only 131 terabyte of addressable memory, which is still okay, right? So however, on ARM, if you compile your own kernel and you take Linux safe defaults, it will produce a memory map which gives you 39 bit of addressable space for user space, which allows you to address up to 512 gigabyte of addressable space, right? So if you run a database and it tries to mmap a file or even a disk, you give it a full disk which is 512 gigabyte or more, it will complain that it cannot allocate memory. Not because there is not enough memory, it just doesn't have enough addressable space to mmap this file. For developers, try to avoid using abounding memory mappings. So maybe it's hard, but try to identify the upper bound of addressable space and compare it to the size of the file you're trying to mmap, maybe to give like more robust error message. I don't know if there is a universal way to do that. In Linux, you can read like the proc file system for that. For DevOps, make sure you review your second architecture kernel. My memory layout configs is 39 bits is too low a bit for user space address for modern workloads, which we did. So we recompiled the ARM64 kernel with 48-bit user space addresses. So we're now having 556 terabyte of addressable space, which is even more than we had in x86. So we're fine here, right? Wrong, but for some reason on this kernel, some workloads started to crash randomly with no particular pattern. We traced it down to Lua code. We're heavy users of Lua in Nginx. Further investigation brings us to this magic Lua JIT light user data model. So we use Lua JIT to make our Lua faster. And most of the code in Lua JIT uses this module, which is a simple and efficient C interface. The efficiency it operates directly on C pointers. But they made optimization. They say that, we know that 64-bit pointers are only 47-bit long, right? So we will use all these and use zeros to store our additional metadata. Yeah, it says in the comment. So this is a link. Yes, it's documented in the comment. So here, 64-bit pattern, 46-bit addresses. Done. So we have this extra bit, 48, right? So the crashes are random because sometimes it gets overwritten, sometimes not. Sometimes it matches what it should be. So yeah. State assumptions in code, not comments, because who reads comments before trying to run the software, right? If they checked it, even if you want to optimize in a way that efficiently run on 47-bit system, you can check this assumption when your process starts and say, hey, I only run on 47-bit addressable system. Sorry, bye. And we don't have to spend like 3 weeks to debug this. Don't over-optimize. Probably reusing zeros in C pointers is quite a bit of a stretch, right? Or if you do want to optimize, provide a fallback generic implementation. Same for DevOps. I mean, both ways. Second, page size. When somebody wants to optimize size, it's all about page size somewhere, right? So what is a page size? It's a minimum discrete block of RAM you can get on a system. Usually you shouldn't care, but many database workloads try to keep track of allocated pages. For example, like for faster sequential memory access, avoid memory fragmentation, and efficient memory reuse, right? So this was for us. Your mileage may vary. So the process uses much more memory on secondary architecture with the same data set. But otherwise, it works. Like, it doesn't crash. It works as intended. But it depends on the efficiency of implementation of this page size-centric algorithm. And the cause is the process has hard-coded page size in code. Because on x86 system, it's always 4K, right? Why do we care? But on ARM, you may configure different page sizes. You can have 4K, 16K, and 64K pages, depending on which memory layout you choose. So we were running at 4K pages, but we had to switch to 16K pages to allow us to have 48-bit addresses. So this is the picture you may get. So this is a typical tracking on x86 system. So you requested 3 pages, you got 3 pages, nice continuous memory, fast access. If you try to run the same on ARM64 with 16 pages, you get something like that. You might get something like that. It's still variable. So here you have non-sequential access, memory fragmentation, and not efficient memory use. So all you've been fighting for, you kind of lose in one go. Don't do this. 14,000 exact string matches on GitHub, which people do this. Do this instead. Like, just ask your operator, saying, what is my current page size? And build your algorithm on top. Or even if your algorithm is tightly bound to 4K pages, do this on the start of your process and say, like, an error out saying, this software efficiently runs only on 4K pages, or even a log warning would be fine. As a DevOps, we have to monitor process memory uses on different architectures, compare them, and search for anomalies. The next is file system block size. It's like page size, but for files. It's a minimum amount of piece of data a file can occupy on disk. So even if you write 1-byte file, it will occupy at least block bytes, right? So typically, your there is a logical file size and a physical file size. So physical file size will always be larger than your logical size, almost always. Except, and the file system block size is usually a multiple of the underlying block device block size. It can't be less than that, right? And the file system block size is mostly useful for sparse files. Anyone doesn't know what a sparse file is? So sparse files are files with many zeros, big files, but have a lot of zeros, are mostly empty, right? And modern file systems are smart enough to say, hey, I will not write all these zeros to disks. I will just write some metadata that the next range is a big zero hole, right? So in this case, this is the opposite case where your file system physical file size is smaller than the logical file size because we don't record any useless zeros. So for us, the symptom was the software worked fine, but the test suite for Captain Proto, it's like a protobuf messaging solution we use, just fails on ARM64. And it fails in an interesting way that this test fails only if you run the test suite from TMPFS and not from any other file system. Because that the test runner has hard-coded block size, because it's for all file systems you can imagine in Linux, it's always 4K by default. But on memory-backed file system, the block size equals space size, and we already know that ARM64 can have 16K pages, right? Don't do this. Do this instead. Just query your file system. What is your current block size? Easy. So that's basically it. So the conclusions here is that even portable code with no assembly in it, even written on Python, can fail in many ways on a different architecture. For developers, the advice is don't over-optimize. Provide fallback implementation if you over-optimize. Don't rely on assumptions. State them in code, not in comments. And also, if your assumptions do not hold, provide meaningful error messages so people immediately see. So, cannot allocate memory is not a meaningful error message with plenty of memory in the system, right? For DevOps, we ensure that the CI environment can test diverse set of architectures and configurations. Even if you don't plan to run a second CPU architecture anytime soon, add support for cross-compilation in your project, test it in CI, and you will be ready. As the project evolves, you will be sure that it's ready to be cross-compiled to a different CPU architecture. And maybe provide tools and linters which enforce best practices, some of an advice which I provided here in code and build systems. So yeah, after resolving all this, this is our ARM server in production now. It's almost identical to the x86, so some people even can't tell the difference when they SSH in. So yeah, that's it.
We got time for a few questions.
Yep. Any questions?
Did you consider to make your ARM64 kernel look more like your x86 kernel, using actually 47 bits of memory, which would have avoided 2 of your problems?
In kernel configuration, you can't choose any value you want. You can choose a predefined set of values which is applicable to a target platform. So for ARM64, you can have 39-bit addressable space or 48, but not in between.
Oh, there was no 47-bit
yes.
option.
So to be honest, originally it took us so long to debug this issue, so we actually patched the Linux kernel to limit user space addresses for the time being to 47 bits, just to keep us going. But yeah, and the second part is addressable range is very tied to the way how you configure memory management and the levels of page tables in your system. So we haven't tested it, we haven't compared, and I don't have meaningful metrics now, but ARM vendors advise you to move to 64 kilobyte pages for faster memory access, because the memory access in ARM is not as efficient in x86 for 4K page range. We have to yet to test it, actually.